We turn to Chapter 6, which deals with, of course, your favorite planet and mine, the Earth. All right, so let's get into this. There's a nice picture from space, of course, of our wonderful blue planet. Um, all right, so we're really gonna dive into understanding the Earth. Um, all right, so let's get into this. This is a nice picture of Earth as seen, you know, from space, but looking at it in terms of, um, you know, the rocky world that it is. Of course, the Earth is covered by the ocean. Um, you know, 71% of the surface of the planet, but underneath that surface is rock. And rocks of different materials. We'll go into a little bit of that, but not specifically. All right. Anyhow, just a little bit of what the Earth is made of. Uh, not really the minerals. Not too much anyway. So the Earth is the first of the first one that we're going to study of what are called the terrestrial worlds. Of course, that's really an indication that it's a rocky world. So terrestrial or rocky world or inner world is and of course it's the largest of them, of the four of them. We'll get much more into that a little bit later. All right. So anyhow, um, of course the Earth has a moon. It only has one moon. Unlike some other planets, there are of course some planets with no moons at all, and we'll explore that as well. All right. So the moon the Earth goes around the sun. Um, it spins around on its axis, once a day, which we call a 24-hour period. Um, and we'll stick with that, right? So we'll definitely use 24 hours. At any rate, by the way, that it's not exactly true, and that's kind of why the year is not exactly 365 days. All right. Anyhow, so the sun is moving. So the Earth is moving around the sun. We know the distance from the sun. The average distance from the sun is about 150 million kilometers, and it takes a year. So if we converted 150 million, and think about this, the circumference of the Earth travels. So that would be 150 million kilometers times 2 pi. That's the entire circumference. And then it does that in a year. If we divided that by the number of seconds in 1 year, you'd get approximately 30 kilometers per second. And I'll try to do that, a video on that a little bit later. All right. So anyhow, some other things about the Earth, of course, is and it's not the only planet with an atmosphere, but it's certainly it's a very unique atmosphere to us. There's this wonderful, as they correctly point out, a blanket of air. Turns out to be mostly nitrogen. We'll discuss that in more detail, and also a magnetic field. We don't really think about, but is actually the air and the magnetic field are actually protecting us from space. I mean, we would not be alive if it wasn't for the magnetic field of the Earth, and of course the atmosphere. We need the atmosphere to breathe, obviously, but it does so much more than that. It protects us from harmful radiation from the sun. It breaks up most of the material that hits the Earth. The material that's floating around in space or traveling around in space. Usually, it's these little micrometeorites that if you look up in the night sky and you see this flash of light go across the night sky, they call that a shooting star. It's nothing to do with stars. It is a small piece of usually some rocky material that hits the Earth, and what happens in the atmosphere is our atmosphere will cause friction and cause the, if, let's say, imagine some object coming in and it's traveling really, really fast. It hits our atmosphere and begins to slow down because of friction, and most of the stuff burns up in the upper atmosphere, and that's the little streak of light that you see. Occasionally, those things will hit the ground, and we recover them. Sometimes we recover them as meteorites. All right, so we'll get into that a little bit later. All right. Now, of course, the Earth is spinning around on its axis. If you were looking down from space, the Earth spins counterclockwise, right? So it's spinning counterclockwise. If you imagine you're above the North Pole looking down on it, and we also go around the sun in that same orientation. We go around the sun counterclockwise. So what that means, of course, is that we're spinning from west towards east, right? And so that's why, when people talk about the sun rises in the east, it's just us rotating into that direction. And so that seems like the sun is rising in the east and setting in the west. All right, so anyhow, so the Earth and most of the objects in astronomy are large enough, and not everything, by the way. The asteroids will not be included. Most of the asteroids will not be included in this, but things that are large enough to self-gravitate, that they will become spherical, more or less spherical. Let me put it that way. They're not always perfect. In fact, you rarely find perfect spheres. In fact, the Earth is a little bit wider along the equator than it is the direction from the center of the Earth towards the poles. So the distance from the center of the Earth to the equator is a little bit longer, as you can see there. It doesn't look like it's much, but it is technically. Like if you looked at that, it actually has a name. It's called an oblate spheroid. All right, so that's and the result. Remember, we talked about this before about inertia. That objects want to continue in a straight line motion unless there's a force that acts on them. And so the Earth, of course, has a great amount of mass. And that mass wants to keep going in a straight line, and so this bulging at the equator is due to inertia. All right, so that's that shape, that oblate spheroid shape of the Earth. All right, so now we're going to go into the Earth and think about the Earth just as in terms of just the elements on the periodic table. I want everybody to understand that this has nothing to do with how these elements bond together. Not yet anyway. We're going to get into that a little bit. But if you were just to count the, as far as the atoms that make up the planet Earth, almost half of the atoms are actually oxygen. Now they're locked up into rocks for the most part. A little, very small fraction, as a matter of fact, is what our atmosphere is. But most of the mass of the planet, 45.5%, is composed of the element oxygen. Then comes silicon, right? Little more than one fourth. Then comes aluminum, and then iron, which is that's going to come back. We'll talk about why we find so much iron on the planet Earth as well. Then comes calcium, and then magnesium, and then less than 1%, or around 1% or so, everything like all the other elements practically all the elements. There's a few that are not actually on the Earth. One is called technetium. The other is promethium. The reason that they don't exist on the Earth is because they don't have any stable isotopes. They they were probably there at the very beginning of the Earth, but they're naturally radioactive, and they've decayed away and become other types of atoms. All right. So anyhow, so these first two, oxygen and silicon, make up what are called silicates, right? And the most common silicate that we find on the Earth, of course, is sand, right? Silicon dioxide. It's also known as silicon dioxide. Um, it's also known as the mineral quartz. I mean that's literally what sand is made of, right? Is silicon dioxide. So it's a silicon atom bonded covalent. Not that this isn't a chemistry class, but it's bonded covalently with two oxygens. That's what that's talking about. All right. Let's see what else. All right. Let's move on to the next slide here. All right. So now this is a very common quantity. We use the symbol rho to describe this quantity called density. All right. So density is the mass of something. So that's where the M comes from, divided by the volume of something. And so the volume here. This is actually a very common geometric formula. 4/3 pi times the radius of the object to the third. That's the volume. So it's really density is mass divided by volume. This 4/3 pi r cubed. Sorry if I said pi r squared. It's 4/3 pi r cubed is the volume of any sphere. So if you measure the radius of the sphere, or you know the radius of the sphere, you can figure out the volume of it. All right, and again, I'll do some examples of this. We do examples of this in lab as well. All right, so just to give you a sense of density, and we normally will measure the mass in grams. Sometimes, very rare. Well, I shouldn't say rarely, but sometimes the mass will be measured in kilograms, and if that's the case, the radius will be measured in meters. But for the purposes of what we're doing right here, the mass is going to be in grams, and the radius is going to be in centimeters, and of course you have to cube that. So when you measure the mass, and the reason that we do it in grams per cubic centimeter is because the density of fresh water, all right, so liquid fresh water, right, which is different than salt, frozen or salt water. So fresh liquid water has a density of 1 gram per cubic centimeter. All right, so that's why we use this as we try to compare the density of different objects, including entire planets, to the density of liquid water. All right, and we're going to see a huge trend in our solar system. Right, this is a big idea: is that the density as you get closer to the sun, the density of the planets is large, and then as you get further from the sun, the density goes down. That's the overall trend. In fact, that's one of our labs as well. All right, so but the overall density of the Earth is about 5.5 grams per cubic centimeter. And you pick up the average rock on the surface of the Earth, and the density of that rock is around 3 grams per cubic centimeter, sometimes a little more, sometimes a little less. And then if you take a piece of iron, just a solid piece of iron, the density is around 8. It's actually about 7.9 grams per cubic centimeter. And so if that's true, right, if the average rock is this, and water is 1, and the iron is close to 8, then how did the Earth have a density of 5.5, which is much greater than the average rock on the ground? And so there must be a lot of iron in the Earth. That's the point of this. There must be a huge, and that's what most of the core is made up of, is iron. All right, so we'll